Okay, great. So let's go back to this. Okay, so look, this is the potential at the surface of the sphere. Okay, k cosine 3 theta. And it wants you to figure out the potential inside and outside surface charge density. We'll get back to the surface charge density. Let's start with potential inside and outside the sphere. Okay, so why don't we begin? Let me show you how to go about doing this. It's very simple. It's just thinking critically. That's it. Let's begin with wait, where's the pad? Okay, let's begin inside the sphere. So we have a sphere, radius r. This is the radius r, and we have a surface charge density on it, v0 cosine 3 theta. Okay, so let's first take the case if we're inside the sphere. So this is r less than or equal to r. Okay, so we are inside the sphere. Now think about it. If we are inside the sphere, if we're inside, you don't want r to go to 0, because at r equals 0 the potential will blow up. Anything over 0 is infinity. So that means for this not to happen, so we don't get into a situation like that, we had to set BL equals 0, because that would take care of this term. So inside the sphere we have to set BL equals 0, and as such we get VR theta equals summation L equals 0 to infinity AL RL PL cosine theta, which are the Legendre polynomials. Okay, now so this is for outside the sphere. What about inside the sphere? Inside. This is inside. What about outside? What if we are outside the sphere? What's gonna happen? Well, outside the sphere, you don't want the r to go to infinity, because if r went to infinity, here you don't want r to go to 0, so you eliminate the term that can get you into that scenario. Here, if r goes to infinity, the potential would go to infinity, right? Because L is positive, and you don't want that to happen, so now you set this guy equal to 0. If AL equals 0, then this doesn't happen. So that means the potential outside will be BL over R to the L plus 1 PL cosine theta from L equals 0 to infinity. So this is outside the sphere. Okay, so now the question becomes, what are these coefficients AL and BL? And for that, we have to turn into the boundary conditions. Right? For that, we have to turn into the boundary conditions. Now, does this help or no? Do you know what to do from here, or should I keep showing you?
So basically, if it's you choose the boundary conditions based on which ones are defined and give a reasonable result.
Yeah, exactly. So far, that's what we've done in order to see what expression could we fit for the potential inside the sphere, and what expression could we fit for the potential outside the sphere. That is correct. You wanna give it some thought what happens from here, or you want me to keep showing you? I'll show you what we mean. Let's restrict. Let's go first inside the sphere. Okay, So inside the sphere, okay, we already found what the potential is, generally speaking. It's the one in blue. Okay. And we can say what happens at the surface. So now we invoke the boundary conditions. On the surface, VR equals theta. So I replace small r with capital R. Okay. And if I do that, then I get the summation from L equals 0 to infinity. AL, RL, PL cosine theta. And keep in mind what the objective is. The objective is to find out what those ALs are, because those define your potential. And I know on the surface of the sphere, this has to equal K cosine 3 theta. K cosine 3 theta. Okay, now using trig identities, if you let's play with this cosine 3 theta a little bit. This is V0 theta equal cosine 3 theta. If you play with this a little bit using trig identities, you will find out that this is expressed as a linear combination of k, there's a k here, okay, of 4 cosine cube theta minus 3 cosine theta. Okay, this is a third order polynomial. Okay, and I know that a third order polynomial, I know that the Legendre polynomials are a complete set of polynomials, which means I could take any third order polynomial and express it as a combination of the first 4 Legendre polynomials, right? And I know that since the degree of this polynomial is odd, because I have 3 and 1, right?
Yeah.
I only need P1 and I need P3. Okay? Where I could somehow multiply this by alpha. Now this is all math stuff. Okay? I could multiply the first one by alpha and the second one by beta. Okay? And that should get me the Legendre polynomial that I'm at, which is 4 cosine cube theta minus 3 cosine theta. And now we can solve for alpha and beta, you know, using straightforward algebra. So so from here you know how to solve for alpha and beta. If you have a first, what's the first degree, you know what the first degree Legendre polynomial is, yeah?
That's X. There's a, well, they give you a table.
It's yes, but this is in terms of theta. Yes, it's cosine. It's cosine theta. So alpha cosine theta. Yeah, I mean yeah, alpha cosine theta. Yeah, plus beta. What's the third Legendre polynomial? Third degree Legendre polynomial. That's half 1/2 3x squared minus 1/2 I believe 5x cubed minus 3x. Yeah, he'll give you this. You know, I don't think you have to remember that. So this becomes 5 cosine cube theta, right? Minus 3 cosine theta.
Okay.
Okay. This half multiplies both, so I need a bracket here, and then I need another bracket here. Okay, and this has to equal 4 cosine cube theta minus 3 cosine theta. Okay, now I can collect the terms and I can solve for alpha and beta. So from here on, this is straightforward algebra. A FOIL in the half and the beta, you get beta over 2 times 5. So wait, let me do this. 5 halves beta cosine cube theta minus, I'm gonna collect the terms that have cosine. So I have this has cosine and this has cosine after I multiply it by the half and the beta. So I get I'm gonna pull the cosine outside and I'll get half minus 3 over 2 beta, and this has to equal 4 cosine cube theta minus 3 cosine theta. Right? So the coefficient multiplying the cosine cube has to be the same on both sides. So 5 halves beta has to equal 4, which means beta has to equal 8 fifths. And so this is beta. And then this guy here, the coefficient of cosine has to equal the coefficient of cosine. So we get alpha minus 3 halves beta equal minus 3. Yeah. Solve for, you already found beta, plug it in and solve for alpha. So alpha 3 over 2, beta is 8 fifths, right? Equal minus 3. So this is what, minus 3 plus we get here what, 4, 12 over 5 plus 12 over 5. So what's this? Minus 8 plus wait, 4, yeah, no, minus 15, minus 3, yeah, minus 3 fifths. So we found, so this is your alpha. Okay, so why did I do all this? Why I did all this in order to figure out, in order to break this into two different Legendre polynomials, alpha and beta. So I can now say that v0 theta, yeah, is equal to k times alpha p1. Remember, I'm plugging in here now. So alpha turned out to be minus 3 fifths. Minus 3 fifths. First Legendre polynomial, yeah, which is p1 cosine theta. And then the second one turned out to be 8 fifths. So I'll leave the k outside. Plus 8 fifths. And that's the third Legendre polynomial, cosine theta. There we go. Here we go. Yeah?
How do we know the
Okay, so if you want to know, I'll show you. Cosine 3 theta is the same thing as cosine 2 theta plus theta. Do you agree to that? Isn't 3 theta just 2 theta plus theta?
Cosine, yeah, of course.
Okay, FOIL this. What's cosine A plus B? It's cosine A, cosine B, minus sine A sine B. Sine 2 theta, sine theta. Okay? Okay, now what's cosine 2 theta? There's a trig identity that says cosine 2 theta, this guy.
The sine theta.
Huh? There's a trig identity that says cosine A plus B is cosine A cosine B minus sine A sine B.
Right. Yeah.
So now there's another trig identity that says cosine 2 theta is 1/2 1 plus the other way around. It's 2 cosine square theta minus 1. This is cosine 2 theta times cosine theta. Okay? Minus. Now, there's a trig identity that says sine 2 theta is 2 sine theta cosine theta times sine theta. Okay? The objective is to get everything to cosine. Okay, so if you FOIL cosine here, you will get 2 cosine cube theta minus cosine theta minus 2 cosine theta, and you have sine, this becomes sine squared.
Yeah.
Okay, now I will change this to cosine. So the first two terms remain the same. So let me start from the beginning because this will get a little long. So 2 cosine cube theta minus cosine theta minus 2 cosine theta. Now there's a trig identity that says sine squared plus cosine squared equals 1. So sine squared theta becomes 1 minus cosine squared theta. You follow?
Yeah.
Okay, now FOIL this in here. So you get 2 cosine cube theta minus cosine theta minus 2 cosine theta plus 2 cosine cube theta. Now collect the cosine cube. 2 cosine cube plus 2 cosine cube is 4 cosine cube theta, and minus cosine minus 2 cosine is minus 3 cosine theta. This is exactly what I wrote. I went to right away without doing the in-betweens.
Okay.
This is what I have on that other page.
Yeah. All right.
But it's basically straightforward trig identities. Math trigonometry below freshman college.
Right.
Okay, so back to the back to here. So so that's the reason why I went to it right away, because I know he may not ask you something like this on the test. This is just math.
Right.
So I went straight to it, if you notice. I just wrote it.
Yeah.
And then this whole thing is multiplied by k, and then from there on we invoke Legendre polynomials, and we already discussed what happens afterwards.
Yeah, although I don't remember him. I don't think that we're going to be doing a lot of trig identities. Like there's going to be some here and there, but I don't remember.
Right, but
he would just give you the.
Yeah, but he could give it to you like this. He doesn't have to make the question long. He, instead of giving you cosine, where is it? Instead of giving you cosine 3 theta, he can just simply give you the result.
Oh yeah.
Yeah, there's a million ways to ask the question in a short, concise way. Okay, so now we are down to here. So now we have the surface potential in terms of our Legendre polynomials. Okay, so now back to this equation. Oops. Back to this equation now, right? Here, the first one inside. So I'm going to replace this with what I expanded this into. Okay. So we've got k summation. So let's go back to this color. Summation from L equals 0 to infinity. AL, we're on the surface, so this is RL, right? PL cosine theta. This has to equal the surface potential, which is this guy here. Sorry, my pen is acting weird today.
Wipe the tip off, that would work better.
Let's see.
If you like wipe the tip off or something, it might have got like dirty or something.
I don't know, sometimes it's let's see. Okay, so
sometimes if you get oil or something, or grease or something on the screen or on the, it's like a touch screen. It can mess with the conductivity. Like sometimes when after I eat pizza, I can't use my phone. Like I grease on my hand. It's like an insulator.
True. Okay, so this has to equal my surface potential, yeah? Which is minus 3/5 k P1 cosine theta, yeah? Plus 8/5 P3 cosine theta. And now we need to get the coefficients. Wait, this is AL here. There's an L here. Okay, I need to get the ALs out of that. And how do I do that?
Divided by AL.
Here I use a trick similar to the Fourier trick, if you remember. What I would do is to multiply both sides, right, by the remember, the Legendre polynomials, just like the sine, the sine Fouriers are orthogonal functions. Meaning what? Meaning in general, the integral from -1 basically what I would do, let me just show it to you in a little bit of better steps here. What you could do if you have a PL, yeah, of x, you could and then on the right hand side you have PL cosine theta, right? Of course, if you let x cosine, then if you let u to be cosine, then du will be minus sine. So you will have here sine theta d theta, right? So what you could do is you could multiply both sides of this by p prime L of x, which would be p L prime of cosine theta. Let me move this a little bit left. Right? Sine or cosine theta. So you multiply both sides by PL prime cosine theta, sine theta d theta, right? And there's a dx here. And what you do is you integrate both sides from -1 to 1, and this gets integrated from 0 to pi. Now, how is this helpful? This is helpful because what's the result? Well, the result for all the L primes that don't equal L, the result is 0, and only the term where they're equal, it picks up only the term where they're equal, and the answer is 2 over 2L plus 1. This is the Fourier trick in Legendre polynomials. You understand what I'm saying? So following this trick, we can eliminate all the L's except for a couple of L's that we can solve for. You understand?
Okay. Oh yeah.
So basically we multiply by PL prime cosine, sine, and we integrate both sides.
Yeah, it only has an actual value when the L's equal each other.
Right.
All right.
Exactly. So now, you know how to implement this on our equation? You want to try?
I think so. So
Okay, look. Look what I could do. So I'm going to go back to my original, which is this guy here.
Yeah.
Okay. Let me paste it below. So let me copy it here. Fair? Okay. And what I'm gonna do, let me bring this easier than having to write this whole thing all over again. So what I'm gonna do, I'm gonna multiply both sides of this by what? By P. So let me do it in a different color. So P L prime cosine theta, right? And then I'll do the same thing on this side. And then of course with sine theta d theta. And then I'll do the same exact thing on this side. So PL prime cosine theta sine theta d theta. And now what I'm going to do, I'll integrate both sides. And then I can integrate this whole side. And what did we say this does? This picks up only the terms where the L's are the same. So let's say L prime is L equals L. So what do you get? You get AL from the left hand side, RL 2 over 2 over 2L plus 1, right? This is the left hand side. Let's move it a little bit to the left.
Oh, so you do them one time.
I mean, in the same step, and now I can distribute the integral, and of course I'm integrating from 0 to pi on both of them. Right? This is the Fourier trick. So I get minus 3 over 5k P1 cosine theta PL prime cosine theta sine theta d theta. That's one from 0 to pi, right? Plus the other one, plus 8/5 k. Oh, I forgot the k here. There's also a k here. So 8/5 k, right? Keep it outside the integral. P3 cosine theta P L prime cosine times sine theta d theta from 0 to pi. There you go.
The team viewers
Oh, it did disconnect.
Yeah.
Let me see. Mine is up. You got it?
Let me see.
Okay. And now here, you wanna attempt? What's the integral of this? Those can be integrated explicitly. You wanna try? From here, what you get? Well, I was able to get the AL out of the summation because all the other terms vanished. The only one that survived is when the L equals L prime, and the answer for that is just 2 over 2L plus 1. And then on the right hand side, so now the left hand side stays the same. Okay, great. Let's look at the first integral. Which term will I pick up? I will only pick up the first one. When L is 1, because only when this L prime is 1, I will get an answer. We said on every other L, the answer is 0. Right? So,
L has to be 1.
well, otherwise the integral is 0. That's what I just explained to you. The only way this survives is when L is 1. And when L is 1, what will I get? I will get 2 over 2L plus 1, just like I did just like I did on the first one.
Right. For that one, it's, yeah, because we're doing L. Yeah. Okay, yeah.
From 0 to pi. And then, let's go...
Yeah, you just basically plug in the...
Right, and let's go to the... Yeah, exactly. And let's go to the second one. What will I get on the second one? So basically we call this, so this is 2 over 2L plus 1, and we call this delta L1, meaning it will equal 0 if L is anything other than 1, and if L is 1, you will get 2 over 2L plus 1. Okay, and similarly on the right hand side for this guy, which term will I pick? I will pick the L equals 3 and everything else will be 0. So this will be 8/5 k times 2 over 2L plus 1 multiplied by delta L3, meaning this will be 0 for anything other than 3 and 2 over 2L plus 1 when L is 3. Okay, so now I can simplify this result. So I'm solving for AL. So AL will equal to 2. So let's flip these. So this is 2L plus 1 over 2. Right? R to the L. Right? And then we have k over 5. K over 5. I just factored out k over 5. Okay. And I have 2L plus 1. So what do I have left? I have left 2 over 2L plus 1, if I factor out the k over 5, times minus 6. Let me put... this guy is slow. So, k over 5, I have a minus 3 here, and a 2 here, right? Delta L1, plus, I factored out the k over 5, 8, times 2 over 2L plus 1, delta L3. Okay. Now, um, let's factor out 2 over 2L plus 1. So we have 2L plus 1 over 2, 1 over RL, R to the L, K over 5. I will factor out 2 over 2L plus 1 from this. And then I have left minus 3 delta L1 plus 8 delta L3. Okay, now notice these two guys go away. And what do I have? I have left K over 5R to the L. This is for AL. I'm solving for my AL. Right? Let me flip those terms so I have the minus in the middle. So 8 delta L3 minus 3 delta L1. Okay, well, so what does AL equal to? Well, if L is 3, this guy is 0, of course, because we said anything other than 1 is 0, and you get 8K over 5. This guy will be 1 in that case, right? R cube 8K over 5R cubed. That's if L is 3. But now we have to also consider the other way around. What if L is 1? Then the first term goes to 0 and the second term survives. And so I will get minus 3K over 5R to the 1. 5R. So these are my coefficients. Okay? These are my coefficients that I've been trying to solve for all this time. So now I can take those and I can plug them back into my V, because notice that this is the only thing that was missing for me to solve for my potential. My potential was AL RL PL cosine theta for inside the sphere. So now I can plug them back in. And if I plug them back in there, what do I get? I get my V R theta, right? Equals to, if L is 1, I get minus 3K over 5R, right? P1 cosine theta. Because remember, there's only 2 terms that survived from this entire summation, which made sense because anyways, on the boundary condition on the surface of the sphere, we only had a Legendre polynomial that was the summation of 2 polynomials. So that's the first one, plus now if L is 3, the second term of the summation is 8K over 5R cubed, right? And then we had outside a, wait 1 second, we had R to the L. So that's R, right? I think I forgot an R here. Yeah, because this is R to the 1, right? Yeah, I forgot a small r here. Of course, this depends on how far you are from the center, right? Plus times here, it's an r to the L, which is r cubed, because L is 3, P3 cosine theta. Yeah? You could plug in what P1 cosine theta is and P3 cosine theta is and simplify the answer further. Not needed. You could do it if you want. But basically, this is my potential inside the sphere. This is for R less than big R, or equal, of course. Oops, this is a little bit slanted. Do you want to try outside the sphere now? Remember, we still haven't done outside the sphere.
Yeah, let's try that.
Okay. Well, look, think about this. The potential does not suffer any discontinuity at the border of the sphere. In simple words, the potential has to be continuous across the surface.
Yeah.
Which means the potential, you know here how I solved for two different potentials? One inside, one outside?
Yeah. The potential just becomes continuous on the inside. I mean, it just becomes uniform on the inside.
Well, at small r equals big R, they have to be the same.
Right.
At r equals big R, they have to be the same.
Right.
Right? Okay, so that we can exploit that to find the BLs. So we can say VR theta continuous across the surface, which means they have to be equal when small r equals big R. So that means we got for small r, right? Where's here? Which means if this is true, then I could write that AL summation AL RL PL cosine theta has to equal, right, BL over R to the L plus 1 PL cosine theta. Okay, but I've already found out what this is. This is supposed to be big R because I replaced small r with big R. Okay, but I already found out what that is, so I could just plug it in. Right? There's a summation here. Right? So that means BL, well, I mean, there's only two terms that survived, the L equals 1 and the L equals 3, and since they're equal, the coefficients of both series on the left and the right has to be the same, and if that's the case, I could figure out what my BL is from here. You want to give it a shot, or you want me to show you from here, like, what should we do? Which means what I'm trying to say is we already solved for the right hand side, for the left hand side.
Yeah.
At r equals r, what does the left, what's the left hand side? It's minus 3k over 5r. It's just this red box above.
Yeah.
Except you replace small r with big R, yeah? R,
Yeah.
P1 cosine theta plus 8k over 5r cubed, r cubed, notice these go away, P3 cosine theta, and this has to equal to the summation of BL over R to the L plus 1 PL cosine theta. Now again, only two terms survive. On the first one the L equals 1, and on the second one the L equals 3. Because the rest of the coefficients have to be 0, right? Because the rest, there's no P2, P4, P0, P5, P6, so on and so forth.
Right, even.
Meaning there's really only two scenarios here that can happen. If L equals 1, right, then we get what's if L equals 1, we get minus 3k over 5 P1 cosine theta equals B1 over R cubed, if R squared, sorry, P1 cosine theta. This is cosine theta. These two go away, and B1 equals minus 3k R squared over 5. That's the first B. And if L equals 3, then we equate that to the third Legendre polynomial coefficient. So we get 8k over 5 equals B3 over R4, right? I cancelled out the the Legendre polynomials because they're the same on both sides, just like the L equals 1 case. So what do I get for B3? I get 8k R4 over 5. So that summarizes that BL has to equal minus 3k, just like AL, we'll write it the same way, over 5 if L equals 1. If L equals 1, and 8k R4 over 5 if L equals 3. So these are my B coefficients. Yeah? And now I can plug that into my B outside potential to find out my potential is. So finally, VR theta is equal to the summation. Well, there's only two terms in the summation, L equals 1 and L equals 3. So for L1, we get BL, which is minus 3k R4 over 5. Sorry, R squared over 5. Right? That's BL. And if you remember, next to it there was an let me see what was next to the potential inside. I mean outside, over R to the L plus 1, so that's R squared. So 1 over R squared and this is P1 cosine theta, and we know what that is. If we want, we can just plug in. what that is. And then the second term that survived in the series is when L equals 3, so that's plus 8k r to the 4 over 5, 1 over r to the L plus 1. L is 3, so this is r4 p3 cosine theta. So this is the potential outside the sphere. This is for r greater than or equal to r. Exploiting the continuity of the potential across the surface. Questions on this one, Ben? Okay, the last part of the question is asking for, I mean, if you don't have any questions on this, the last part is to find the charge density on the sphere. There is no charge outside. All right? So how do we do that? How do we find sigma? So the last part of this question, it might depend on the angle. It's not going to depend on r because it's on the surface. So it's a function of theta. What is it? Think about it. So the potential, what the hell is this? The potential is continuous across the surface, correct? What's discontinuous across the surface? The electric field. So we built E is what's discontinuous across the surface. And what's E? The gradient of V. And how is V changing? Look at the equations. V is changing as R changes. There's an R here, and there's an R in the first one. So the gradient, which is the change in the rate of change of the potential across the surface, is what's discontinuous. And what's it equal to? Well, remember Gauss's law, EdA or EA equal, right, sigma A over epsilon. So if you cross these out, you get the change in E, right, which is the gradient, is equal to sigma over epsilon. So basically what I'm trying to say is we get it from the discontinuity of the gradient of the potential. So dV outside, out, over dr, right, minus dV in over dr at the surface, when r equals r, has to equal the sigma surface charge density over epsilon. We have both potentials in and out. We differentiate them, subtract them, multiply by epsilon, and that's your surface charge density. So let's do it. dV out over dr. So you would differentiate this red box here. So what's that? Minus 3k r squared over 5, all constants. The derivative of 1 over r squared is what? Minus 2, so this becomes plus 2 over r cubed p1 cosine plus 8k r4 over 5. r4 you multiply by, so this becomes a minus 4 here, right? 1 over r5. So this dV out over dr minus, now let's do the dV in. What's the derivative of that? Where's that equation now? That equation is here. So we're gonna get minus 3k over 5r. The derivative of small r is just 1. So minus 3k over 5r. Yeah. So minus 3k over 5r, 5 big R, PL cosine theta. The last term had an r cube, I think. So 3r squared times that. So 3r squared, and there was 8k over 5r cube. Right? P3 cosine theta, and we will evaluate all this at r equals big R. I think I forgot a P3 on this one. Yeah, on this one. Wait, P. Wait, what's this one? Yeah, P. Yeah, there was a P1 cosine theta here. Or wasn't there? Wait. Yeah, P3. And I forgot on the first one. This was a what? A 1? Yeah, P1 cosine theta, and last one P3. Okay, and this whole thing has to equal sigma over epsilon. So sigma will just equal, so multiply this whole thing by epsilon, right? Plug in r for big R for small r, and you get 6k over 5 r squared over r cubed, that's 1 over r, P1 cosine theta. Okay, minus what's this? You get 1 over r, so you get 32 over 5k 1 over r P3 cosine theta. That's the first guy, plus here we get 3k over 5r P1 cosine theta, and on the last term you get 24k over 2 r's cancel, and you get 5 big R P3 cosine theta, close bracket. So add the like terms. What are the like terms here? We have this guy with this guy. So what's that? 6k plus 3k. Is that 9k? Right? Yeah, 9k. So epsilon 9k over 5r P1 cosine, and then these two are the same. So what's that? Minus 32 plus 24. What's that? 56 minus 56. Did I do this? Did I subtract them backwards, or? Oh, no, no, no. There was sorry, there's a minus sign here, yeah, because it's because remember it's minus gradient. So the minus gradient, the potential equals to the change in the electric field. Change in the potential. The electric field is minus gradient the potential. So yeah, there's a minus sign. So it's fine. I could just flip those. So this is a plus, and this here is a minus. So 56 k over 5r P3 cosine theta. And you know, if you want, you can pull out a k over 5r. So epsilon k, right, over 5r, and just bring the positive term first. So that's 56 p3 cosine theta minus 9 p1 cosine theta. I mean, if you want, you can plug in for what those Legendre polynomials are and get it in terms of the angle theta, because we know what those are. But basically, this is the surface charge density on the sphere as a function of theta. Questions on that? So this question really summarized a lot. It had separation of variables, how to figure out the potential inside, outside the sphere, and the surface charge density using the boundary conditions, Legendre polynomials, and discussed some of the continuities and discontinuities across the surface.